Hi, welcome to the astronomy class. Exoplanets are one of the most fascinating areas of research in modern astronomy. The concept of a planet existing outside our solar system was first considered science fiction, but today we know of thousands of exoplanets orbiting stars other than the Sun. The significance of exoplanets in our understanding of the universe cannot be overstated because they offer a window into the formation and evolution of planetary systems beyond our own. At the time of publication of this video, more than 5,700 exoplanets have been confirmed, while billions of others are believed to exist in the cosmos. In this video, we'll learn about exoplanets and explore some of the techniques used by astronomers to find them. Let's begin. According to the International Astronomical Union, or IAU, a planet is a celestial body that is in orbit around the Sun, has sufficient mass to assume hydrostatic equilibrium, and has cleared the neighborhood around its orbit. A body can be classified as a planet if and only if it satisfies all these three criteria. But this also implies that there is no formal definition of a planet beyond the solar system. So more recently, the IAU rectified this issue and came up with a formal definition of an exoplanet. To begin with, any planet which exists beyond our solar system is called as an exoplanet. Most of them orbit other stars, but some free-floating exoplanets called rogue planets are not bound to any star. As of August 2018, the working definition of an exoplanet, as per the International Astronomical Union, is that the exoplanet is an object that orbits a star, a brown dwarf, or stellar remnant, has a mass ratio with the central object below 1 by 25, and has a mass below the limiting mass for thermonuclear fusion of deuterium, which is currently 13 Jupiter masses. Such a body must also have a minimum mass to size ratio, which is the same as that is used for our solar system, which means it must be massive enough both for self-gravity to overcome rigid body forces and for clearing the neighborhood around its orbit. More information about the choice and rationale of these criteria can be found in this publication. The first confirmed exoplanets were detected orbiting a pulsar in the year 1990. 2 years later, a third planet with a mass a little less than twice the mass of our Moon was found in the same system. This pulsar, PSR J1300 plus 1240, is located around 700 parsecs from the Sun and is a millisecond pulsar which rotates 161 times every second. Astronomers know that there are more exoplanets than stars in the universe, and we have just started exploring them. In fact, even the nearest exoplanet orbiting the star Proxima Centauri is more than 4 light years away from us and is capable of harboring life as we know on the Earth. One of the primary criteria used for checking the suitability of an exoplanet for life is to check if it lies in the habitable zone. The habitable zone is the region around a star where conditions are suitable for liquid water to exist on the surface of the planet. It is also known as the Goldilocks zone, where the conditions are neither too hot nor too cold and are perfect for life. Life as we know on Earth to exist and evolve. It is very much possible that even if life exists beyond Earth, it may not be of the same form as we know it. But it is better to start searching for something that is familiar to us, and at least to begin with. Besides this condition that the planet should have a surface temperature such that liquid water can exist, when looking for possibility of life beyond Earth, astronomers often prefer rocky planets, having a size similar to Earth. But most rocky planets have been found to orbit red dwarf stars, which frequently flare up and can therefore destroy any signs of life on the associated planets. Since our Sun has nurtured life on Earth for nearly 4 billion years, conventional wisdom suggests that stars like it would be prime candidates in the search for other potentially habitable worlds. G-type yellow stars like our Sun, however, are short-lived and less common in our galaxy. On the other hand, stars slightly cooler and less luminous than our Sun, called orange dwarfs, are considered as potentially better candidates to look for advanced life by some astronomers. They can burn steadily for tens of billions of years. The longer time period provides enough time for biological evolution on planets around such orange dwarfs. Another added advantage for orange dwarfs is that for every star like our Sun, there are 3 times as many orange dwarfs in the Milky Way, thereby increasing the probability of finding life on a planet around them. But the best candidates of all for the extraterrestrial life are planets around K-dwarf stars. They are in that sweet spot with properties intermediate between the rarer, more luminous but short-lived Sun-like stars and the more numerous red dwarfs. The K stars, especially the warmer ones, have the best of all worlds for astronomers interested in planets with habitability because the abundance of K stars increases the chances of finding life. Based on their similarities with the planets in the solar system, exoplanets have been classified into several categories. For instance, some of them are gas giants such as the Jovian planets. These systems are extremely hot since they often orbit very close to the parent star, while other planets are similar in size to Neptune and Uranus but may have mixed interiors made up of heavy metals in their cores. Similarly, Earth-like planets with a solid surface are called rocky planets, while those larger than Earth are termed super-Earths and vary in size from 2 to 10 times the mass of the Earth. Astronomers employ various techniques for detection of planets beyond Earth. Some of the common methods are direct imaging, transits, radial velocity measurements, astrometry, and microlensing. When a large gassy planet such as Jupiter races around its parent star in a close orbit, the gravitational field around the star changes. This makes the star sway slightly from its usual path. This motion, when observed, reveals the presence of planets around the star even though the planet themselves cannot be observed. The 1995 discovery of the gas giant planet 51 Pegasi b was made using this technique. When astronomers measured the radial velocity of the Sun-like star 51 Pegasi, they discovered a periodic change due to the planet orbiting around it with a period of around 4.2 days. This discovery led its discoverers Michel Mayor and Didier Queloz to the Nobel Prize in Physics in the year 2019. In some cases, when a planet orbits the star, it forces the star into a small orbit or wobble around a fixed point. As observed from Earth, such a star will sometimes appear to be spinning towards Earth and at other times spinning away from it. The motion of a star can be detected and measured by taking its spectrum. Check out our detailed video on spectra, a link to which is provided in the description below. When the star moves towards Earth, the wavelength of the spectral lines in the light it emits move towards the blue end of the spectrum. On the other hand, when the star travels away from Earth, the opposite happens and the wavelengths move towards the red end of the spectrum as shown here. So to find exoplanets, astronomers look for stars whose spectral lines are moving back and forth, since these must be the ones with planets in orbit around them. By measuring the amount of movement of the spectral lines with time, the mass of the planet and its orbit around the star can be determined. Another technique related to the radial velocity detection is to precisely measure the position of a star so that any wobbling can be measured directly. Such observations are known as astrometry. Since stars are point objects for all practical purposes, observations from ground are restricted by the Earth's atmosphere. Nevertheless, astrometry has been used to search for planetary detections around some nearby stars using large ground-based telescopes. According to the NASA website, 3 exoplanets have been detected using this technique at the time of the recording of this video. A more promising method for detecting small Earth-like planets is to look for the drop in brightness they cause when they pass in front of their parent star. Such a celestial alignment is known as a transit. This is like an eclipse where the planet blocks part of the light coming from the star, just like we can see both Mercury and Venus occasionally pass across the front of the Sun. And when they do, they look like tiny black dots passing across the bright surface. During transits, a planet blocks a tiny fraction of the light from the star. If a distant star were transited by a planet comparable to Jupiter, it would cause 1% of the star's light to be lost from view. One gas giant planet found by the radial velocity method has also been detected using the transit method from a ground-based telescope. This planet, now called HD 209458b, is the first transiting exoplanet discovered. Some astronomers have now discovered signatures of water vapors and molecular signatures of titanium oxide in its atmosphere using spectra. So far, more than 4,300 planets have been discovered using the transit method. If a planet can be detected using both the transit and the radial velocity method, its orbit can be determined exactly and the true mass and size of the planet can be found. On the downside, the transit method can only detect very large and gaseous planets from the ground. To detect rocky Earth-like worlds, astronomers need to make use of the data collected by the space-based observatories such as the Hubble Space Telescope, Gaia, and the James Webb Space Telescope. Cutting-edge modern technology has allowed mankind to observe the alien worlds directly. These observations enable astronomers to analyze the light from the planet itself, determine the chemical composition, and assess physical state of these distant planets. But this is an extremely challenging task. At visible wavelengths, a star like the Sun will outshine a planet like the Earth by 10,000 million times. Why? Because planets do not emit visible light. They simply reflect some of the light from the parent star. If, however, astronomers move to longer wavelengths, such as the mid-infrared, the contrast between the star and the planet drops to 1,000,000 because the amount of infrared radiation given out by the star reduces while the planet itself begins to emit. This mid-infrared radiation, however, is most easily viewed from space. At Earth's surface, the signals can be washed out by the infrared waves emitted by the Earth itself. Also, because planets and stars are usually close together, Earth's atmosphere smears their light into a single fuzzy blob. Astronomers have therefore devised techniques to work around these constraints and make direct detections collecting both visible and infrared light. So far, 82 planets have been discovered by direct imaging. If a planet is orbiting a pulsar, it will cause slight anomalies in the timing of its observed radio pulses. As discussed in one of our earlier videos, pulsars emit radio waves at very precise intervals, making them very accurate time-keeping tools, even better than the best hydrogen maser clocks on Earth. So anomalies in the measurement of pulsar timings is used to determine the orbits and mass of exoplanets. Similarly, planets orbiting a variable star can be identified because they cause slight changes in the variability of the parent star. Microlensing relies on the chance alignment of two stars with an observer. As one star crosses behind the other, the star nearer to the observer acts like a lens, bending the light rays so that the brightness smoothly increases and decreases. If a planet is present around the closer star, its gravity will also bend the light stream, causing a spike as shown in this image. Around 230 exoplanets have been detected by astronomers using this method. Here is a distribution curve showing the detection of exoplanets using various techniques we discussed in this video. As you can see, most of the exoplanets discovered so far were detected using the transit method, followed by the radial velocity measurements. Recently, the James Webb Space Telescope has made groundbreaking discoveries in the field of exoplanet research. With its unparalleled sensitivity and resolution, the JWST has uncovered new insights into the atmospheres and formation processes of exoplanets. For instance, it has detected the atmospheric signature of a gas giant orbiting a nearby star, providing valuable information about the planet's composition and potential habitability. These findings have significant implications for our understanding of planetary formation and the search of life beyond Earth. By studying the atmospheric properties of exoplanets, scientists can gain insights into the early stages of planet formation when the building blocks of life were first assembled. The James Webb Space Telescope's observations have revealed the presence of complex organic molecules, the raw material of life, in the atmosphere of some of the exoplanets. The significance of these findings cannot be overstated. They represent a major leap forward in our understanding of the universe and its potential for supporting life. As we continue to explore the vast expanse of the cosmos, we are reminded of the infinite mysteries waiting to be unraveled. To conclude, The incredible diversity of exoplanets serves as a powerful reminder of the awe-inspiring complexity of the universe, from gas giants to super Earths and from hot Jupiters to potentially habitable worlds. Each exoplanet type offers a unique window into the boundless creativity of the cosmos. The search for extraterrestrial life is an ongoing saga, one that is driven by human curiosity and our innate desire to explore the unknown. I really hope you enjoyed this little introduction to worlds beyond our own. Do let me know in the comment section if you liked this video and what other topics you would like us to cover on this channel. In the meantime, share our content with other astronomy enthusiasts and don't forget to like, share and subscribe to our channel. I'll see you next week with another interesting topic in astronomy. Until then, take care.